Well, welcome back. So lecture 15, general relativity. Here we're going to look at the geodesic equation from variational calculus. So just a brief reminder, lecture 14 we explored how to set up the covariant derivative in terms of the Christoffel symbols, and we saw how to calculate the Riemann curvature tensor and so forth. All right. Basically what? In terms of derivatives of the metric. Yeah. And we mentioned the concept of the geodesic as well, and now we're going to return and examine an alternative method of calculation to set up the geodesic equation. All right. As I make this video, I can think of three major ways to do it. One of which we talked about in the previous lecture, right? Just basically calculate your metric tensor, your inverse metric, and just straight up, calculate the Christoffel symbols and proceed from there, right? That's kind of the most obvious sort of, as Carol says, turn the crank, way to do it. The second way to calculate the Christoffel symbols is this variational approach, which I'm about to show you. And then I think the third way would be, if I remember right, appendix, let's see here, appendix, he's got so many appendices. Appendix J here, non-coordinate bases. In this appendix J of Carroll, he shares the what's sometimes called the tetrad formalism, sometimes called the Vielbein formalism, which is sort of the general relativity analog of the Cartan calculus. It's something even a little bit different than that. Involves something called the spin connection, and it opens up other avenues of discussion because it brings in spinners and such. So I'll just say there's that left to talk about, but let's focus on today's lecture. We're going to talk about the variational method to calculate Christoffel symbols, so let's get into it. So the geodesic equation, of course, was this, basically the acceleration of the path plus the Christoffel symbols contracted across the velocity equals to 0. A geodesic is a path which parallel transports to its own tangent vector field, and that means it satisfies that equation there, right? So I'm going to follow the calculation from page 106 and forward in Carroll. And so it begins by looking at time-like curves, right? And if it's a time-like path, you can calculate the proper time by integrating the basically the interval, right? You need this minus here because if it's time-like, that's negative. So this is the square root of a positive number, which is something you can integrate. And so the first order of business is just to try to get rid of that square root. So I don't know if you've ever, well, I'm sure you've done Calculus 1, right? So in Calculus 1, we do maximization problems, right? And like if you're maximizing the distance from something, what's the first thing you do? Well, the first thing I do is make an argument that I could maximize or minimize the distance. I might as well maximize or minimize the distance squared, because the distance squared, it's got no square root, and it's ever so much more pleasant to calculate with, right? And so this is the sort of analog of that thought in the current context, what's going on right here. Because his first order of business is to go, well, if we call this thing f, we're really looking at the variation of minus the square root of f, integrated over the parameter of the curve, which by the usual song and dance, the variation of the integral is the integral of the variation. And then by the chain rule, variational calculus, we've got 1 over twice the square root times the variation of f. But if you change the parameter from lambda to tau, right, or if you just set lambda equal to tau, another way to think of it here, then f is just equal to minus 1, and so the variation of tau just becomes minus 1/2, variation of f d tau. And so in other words, we can study the variation of tau by instead studying the variation of 1/2 f d tau, which is just this, right? Which is like, way easier to do calculus on because it's got no square root and it's, you know, much prettier. Let's get into it. So, oops, sorry about that. All right, so we're going to consider infinitesimal variations of the path. So x maps to x mu plus some, you know, variation x mu, and the metric, you know, transforms to the metric plus this little piece. So, of course, the metric can depend on, the metric generally depends on position, of course, in a curved manifold, so we have to include this term. All right, and Carol says something like, there's no covariant derivative here because we're fixing coordinates and doing this calculation in a given coordinate system. So if that makes you feel better about it, then great. To first order of the variation, we take, all right, so again we're varying I, and so past the variation inside the integral. And then I'm varying this, so I've got a triple product rule. So I've got this times this times this, so I do variation of the metric times the velocities, and then metric, variation of the middle velocity times the last one, metric, middle velocity, variation of the final velocity. And then I make a step here I later regret, which is to exploit the symmetry, because basically these are the same thing with different labels because of the symmetry of the metric and the fact that we're taking the same, it's like velocity, variation of velocity, 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 variation of velocity, right? So there's a symmetry here. I can just combine them and put a 2. And I'll do that, but there's another way I could have gone here. Anyways, the bottom line is I have to undo that in the next page because I did it. So it wasn't as awesome a move as I thought it was going to be. Oh well. Anyway, so then we got this and this, right? So, all right. So to make progress on this, I need to understand that I can use the product rule to rewrite the integral, right? In other words, I'm saying let's do integration by parts, right? But, you know, this is not an integration by parts that you did in Calculus 2, right? So I think just calling it integration by parts and not showing you the details, well, that is customary in physics. It's better for me to show you the details. So let me show you the details. If we take the derivative of this product, like this, and remember this is a notation for a test function, which depends on the parameter as well. If you go back to my lecture on variational calculus and classical mechanics, I kind of gave you some window into how we could formalize this. But anyway, we'll keep it formal here, though. So I got the triple product rule, right? So derivative of the first, second and third unchanged, derivative of the middle one, first and third unchanged, derivative of the last one, first and second unchanged, right? And then one of the interesting things about the variational derivative is it commutes with ordinary derivatives in this sense. So like the derivative of the variation is the variation of the derivative. Let's see here. So this becomes that, all right? And then this is literally that, and then I subtract this to the other side and this to the other side, all right? So the minuses here and here. Now, notice that we have the term right here, right? So like, well, without the 2, of course, but g mu nu, velocity, variation of the velocity, right? That's this term, which is this term, right? Well, modulo of the 2. And then so I can trade this for all of that. But then the thing is, when I integrate this, the integral of a total derivative is just the thing being differentiated, evaluating at the endpoints, right? But we're assuming that the variation vanishes on the boundary of the path we're integrating over, so that drops out. And we're just left with these two pieces, which I've written down here, right? And of course we still have the variation of of the metric right there, right? So let me get my book out of the way here. Scooch this up a bit. All right, so vector philosophy. So product rule, also known as integration by parts, gives me these two terms. This was there before, right? It was there. It's still there. Then I go, okay, so what was the variation of the derivative? Well, it is explained all the way back up here. This right here is the variation of the, not derivative, variation of the metric is right there. So, there it is in all its glory. That's the variation of the metric. And so, lo and behold, we have this, and this, and this, and we can factor out the variation of x nu. Notice that I relabeled sum over sigma to a sum over nu so that it would match this one and that one, right? Because I wanted to be able to factor it out of 3. If you're going to factor it out, you better use the same index of summation. Otherwise, all your indices will be meaningless when you get to the next line. We don't want that. So, moving on here. Here we go. So, notice that the derivative of the metric with respect to the proper time, what this means is we're evaluating the metric along the curve, and so you can expand this derivative with this meaning. This is the chain rule, all right? And great. So I had a dg mu nu d tau on the previous page, and now I'm trading it for a you know, one of these guys. All right, fine. Well, uno momento. Yes. I'm trying to remind you guys where it was remind myself where it came from, right? So this one right here, yeah, that one in the middle. I'm expanding that dude by the chain rule at the top of here, like so. Now I've got velocity. All right. Now these terms are simpatico. And so since this holds for arbitrary variation in the new direction, it follows by general principles of cancellation in variational calculus that implies that this equation, well, that the thing inside must be 0. If the variation of I is 0, it must be, you know, sorry about these, I'll put this 0 here, like so. That 0 is what implies this equation has to be true. And yeah. And then I multiply by the inverse metric, and really I'm contracting across it. Technically I'm adding this equation up after it's more complicated than just multiplying at that. I mean, I'm summing it. There's a summation over nu happening here. There's a contraction, and that contraction results in the Kronecker delta, like so. But if you can see past that little bit of tensor calculus right there, then we isolate the acceleration right here and divide by 2. And so if I divide by 2 here, I have to keep the multiplication by 2 there, which I do. And yeah, and since I put it to the other side, the signs flippy-flop, right? So like this becomes plus 2 minus that, and oh, I'm not, that's not what I'm doing. My bad. This is just, I guess I'm multiplying this equation by -1 or something too, right? Like because I'm putting this term as positive, it was negative before, right? And I divided by 2. So anyway, it's not hard. You can get to here. All right, and then I have to undo that star step by sort of essentially symmetrizing over alpha and beta. Like I can undo this 2 and rewrite it as these two terms contracted against that. So by the same thing I did in the previous page calling star, I can undo star in this step here like that. And when I do that, then I've got, well, I got what I'm looking for, right? Because this is the expression for the Christoffel symbol. But of course, this time we derived it a really different way, right? You know, before we derived the Christoffel symbol by assuming that the metric, that the connection we're interested in preserved the metric, and then that, you know, calculation that I showed you guys from Frankel's book derived this formula for us, basically, right? Or if you follow Carroll, he uses the you know, the covariant derivative for the metric tensor, and again essentially does the same calculation, added 3 different ways, things cancel, and this equation pops out for the Christoffel symbols. So while the motivation looks slightly different, Frankel versus Carroll, it all boils back down to that, adding 3 things together and some cancellations. Yeah. Anyway, so there it is. That's the geodesic equation derived from the variational principle. Now, what's interesting is we'll see that, so sometimes in differential equations we come across a method which is interesting not just because it produces a general formula, but because the method of producing the general formula is of its own right a calculational procedure. A good example of this is, you know, oh, yowzers, what's the name of that stupid thing? The integrating factor technique. The integrating factor technique, right? We multiply the differential equation by this integrating factor, and then wonderfully the reverse product rule happens, and then we can integrate both sides and get a solution, a general solution. And so if you can do that formally and write the general solution as an integral of, like an integral times an exponential or something, right? That formula is actually not so useful. What's useful is the actual, you know, proof that led to that formula, because you can do that proof, and in so doing, you have this sort of redundancy calculation to check what the solution is. If you calculate the integrating factor correctly, like there has to be a reverse product rule that appears, things like that. So in the same sense here, we can vary the action, right? The I, as we called it here. And in varying that, we'll be able to produce something, and then by a process of like comparison, figure out what the Christoffel symbols are. So it's a nice calculation. Although I guess it doesn't. I'm not so sure it has the kind of built-in redundancy I was talking about with the integrating factor method. That's just it just kind of reminded me of that. That's all I'm talking about. Okay, anyway, so properties of geodesics. Geodesics give paths of 0 acceleration. All right. In Riemannian geometry, a geodesic is arc length, or you could say unit speed parametrized. That's a unit speed curve. So, and then sometimes if they're talking about like a curve that follows on the same set of points but has a different parameterization, you might call it like a pre-geodesic or something. I don't see any of that language in Carroll, so whatever. But in Carroll, of course, we're not just looking at Riemannian geometry, we're looking at semi-Riemannian geometry, and we're interested primarily in Lorentzian geometry, right? And so in Lorentzian geometry, we have 3 different kinds of paths. We have paths that are time-like, we have times that are null paths, and we have times that are space-like. Carroll doesn't seem to spend much time at all talking about space-like paths. Pretty much everything I've seen him say anything detailed on, it's been on time-like or null paths, right? Anyway, so let's focus here. Time-like path. So if we have a time-like path, like we just derived, we can use the proper time tau, which is analogous to arc length in this context, as the parameter. And Carroll claims that the geodesic equation can be expressed via 4 velocity as this. It's this was the I think we called this the covariant divergence or something, right? And here's the proof that we can write the geodesic equation as this. Here it is right here. So this is the covariant derivative of the 4 velocity, the proper velocity, right? And then if you contract that thing against it's against the 4 velocity like so, we get this, which actually means this, all right? And of course here over here, well, that's starting to look like the geodesic equation, right? And then we've got some chain rule stuff to do over here. So essentially what goes on is you could have done this more elegantly, I guess, but I got to here and I'm like, oh, well, wait a minute, I'm going the wrong direction. I want to convert the derivatives, I didn't want to get rid of the tau derivative. I wanted to convert everything to tau derivative. So if I'd been smarter, I could have gone right here and gone, oh, well, I can convert this contraction over lambda dx d tau to a derivative with respect to tau of that. And so I could have gone straight from here to here if I wanted to. So I hope, you don't try to, read too much into my calculation. Sometimes it's just that I don't have a clear mind on what I'm doing until I get to the end. So this could be simplified. You could go straight from here to here if you wanted. But anyway, I'm leaving it. And once I get to that, of course, hey, that's the geodesic equation. Set that equal to 0. There it is. So apparently, we can write the geodesic equation as the covariant divergence of the 4 velocity being equal to 0. And if you have a particle with mass m, multiplying the 4 velocity, the proper velocity by m, gives you the 4 momentum. And so really, a particle following the geodesic will follow the equation that says that the covariant divergence of the momentum of the particle is 0. And that starts to sound like something that should be physically meaningful, right? I mean, if you've studied classical mechanics, you know the importance of momentum, right? So freely falling particles keep moving in the direction their momentum points, is what this equation means. So that seems eminently reasonable. Yeah. What's devil's in the details there, right? Because that covariant derivative involves the curvature of space and time. So that's where it's not as trivial as just being classical mechanics, is it? But okay, so null paths. Carroll indicates that there does not exist a unique choice, but it's convenient to use parameter lambda for the path, such that the momentum is the derivative of the position with respect to the parameter of the path, right? And he also mentions that if you do that, the energy is always the contraction of the 4 momentum against the 4 velocity. This works for both null and time-like paths. Either way, you get the energy. All right. Space-like path, I said, I believe equation 3.45 in Carroll could be replaced with this, and then you can go through essentially the same arguments that we already did to, arrive at using tau in this sense as the parameter in the same. Maybe I shouldn't call this tau. Maybe it should be called something else. I don't know. I may be committing a physical heresy by using tau here like this. Okay, so. This is me speculating what Carroll might say if he was to say it, but he didn't say it, so I'm, a little bit, probably should slap a tilde on this or something to be safe, but anyway, the point is just this: time-like, null, and space-like geodesics reasonably exist because the metric of the tangent vector of a path with itself is constant for the metric connection. So it's reasonable to suppose these sorts of things even exist because remember that the derivative, they exist in the sense of geodesics at least, because a geodesic has the covariant derivative of the 4 velocity being 0, right? And so this is 0, that's 0, so all of this is 0, which it makes this be constant. And if this is constant, well, the the inner product of the Minkowski product really. Well, okay, so locally, a Minkowski product is either going to be negative 0 or positive, depending on whether you've got a time-like null or a space-like path. And then he has some other interesting comments here. He mentions that you could think about it and see this. I feel like there's some interesting mathematics here. I don't know. Anyway, I think there's more to think about here in terms of the math, but he mentions you could take any time-like curve, right, and you can replace it with like this light, this jagged, always speed of light, like approximation, like, null like null like null 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 null. And I would point out if you can do it for time-like, you can also do it for space-like null 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 null. And so any time-like or space-like path is, like really, really close to a null path in that sense. So he says that means that we found the path of maximum proper time. And here's something he says. He says, time-like curves cannot be curves of minimum proper time because they are infinitely close to the path of proper time 0. And also the twin, so we talked about the twin paradox a little bit here, which is important to us, right? Because eventually we want to get back to that twin paradox problem for fun at the end. The twin who stays home is on a geodesic, so he experiences more time. So, all right, well, we'll come back to that. So next up, very interesting bit, the exponential map. So the exponential map, remember we talked about you can choose coordinates to make the metric look like the Minkowski metric, and also have first derivatives which are 0, right? But then we learned that we couldn't just manipulate the coordinates in the abstract to force the second derivatives to all be 0. So like there's enough freedom in your choice of coordinates that you can choose coordinates which at a point make the metric become the Minkowski metric at the point, and also that the first derivatives of the metric are also 0 at that point. All right. So this is actually a construction using geodesics to do that, right? So the exponential map here's how it works. Basically, the exponential map maps the tangent space at a point on the manifold to kind of like a little region close to it, all right? So like you can think about this straight line in the tangent space mapping to that curve on the manifold. This green straight line maps to that curve. This purple straight line maps to that curve, all right? How do you define the curves? These curves are geodesics, okay? Geodesics. So here's how you do it. Given a particular k in the tangent space of P at M, right? Particular vector, there exists a unique path, lambda maps to x of lambda in M, for which, and I haven't defined this yet, I'm about to define it, okay? For which dx d lambda equals to k mu at lambda equal to 0 and x of 0 equal to p. And I think I've buried the lead here, like big time. Not just a path. The word I should be putting here is geodesic. Okay, because the geodesic equation is a equation which is second order, and we are specifying its initial velocity and initial position, and so there's a unique solution, right? Now, there's not a guarantee that that solution continues on forever and ever, but if it continues on till time 1, well, let's say till parameter 1, all right, then we define x of 1 to be the exponential of k. All right, so this is a very sort of convoluted way of defining a map, but that's what it is. If you can find a geodesic which takes, k as its initial velocity, and at parameter 1, let's just say time 1 for convenience of exposition, at time 1 it gets it's defined, well then whatever it goes to in the manifold, that's what the exponential of k is. All right. So that's the exponential map. It maps lines in the tangent space to geodesics in the manifold. And by the way, there's a really different definition of exponential than you've seen before, right? Yet it's another example of this general idea of exponential. But anyway, so here's the way to construct Riemann normal coordinates. You find a frame. Let's call it E hat mu. I think I'm supposed to put a hat on the. I'm supposed to put a hat on the indices as well. I tire of the hats. My bad. So if you'll let me skip a few hats here and there. So find a frame at P for which the frame gives you the Minkowski metric for the metric. It basically choose a coordinate system which puts the Minkowski metric as the the metric, and this is of course at the point P. All right, and so if we define exponential of k, well, it's certainly going to also be defined for any. If you think about the way that the differential equation works, then it is fairly clear that if you define exponential of k, you're also going to be able to define exponential of ck for c being a positive parameter between, or non-negative parameter between 0 and 1. And so we can restrict k to be sufficiently small so that the exponential is defined for all k near p, right? That seems like a reasonable assumption. So then, given q sufficiently close to p, well, there exists some vector in the tangent space which maps to q, right? And so we can define x hat of q equal to k mu, like that, of course. And if you look at it, then the geodesic that maps through q has this. This is the coordinates of the geodesic through q, right? And so if we look at the image, right? So if we look at the derivative of this, well, differentiate this twice, of course we get 0, right? But on the other hand, since this is a geodesic, it satisfies the geodesic equation, which means that this is equal to that, right? But if this is equal to that, then lo and behold, the connection coefficients at P, right? The connection coefficients at P must be 0, right? And if that's true, then we can of course calculate the covariant derivative of the metric at P, and that's this. But since it's equal to 0, and this is 0 and that's 0, we just get that the first derivative of the metric is equal to 0 for arbitrary mu and nu. And look, I found it in my heart to put hats on the indices down here. I hope you're happy. So, yeah, there it is. So that's pretty neat. You can always, if you want, you can find a coordinate system at a point for which you have the Minkowski metric as the the components of the metric at the point, and also that the first derivatives of the metric are 0 at that point. So that is a very useful system of coordinates. You'll see Carroll use this again and again to set up certain physical laws and to justify various constructions. And that's common practice in general relativity, to make use of these Riemann normal coordinates like that. All right. So let's go back to our expanding universe example, and we'll actually put into practice this variational approach that we've been talking about. All right. So, so here's the metric for the expanding universe. ds squared is minus dt squared plus a squared, or t, times dx squared plus dy squared plus dz squared, which is more elegantly written like this. We call a the scale factor, right? So if we look at it, we can, again, using the trick we did before, we don't have to mess with the square root. We'll just directly vary the basically the gij times a half for the metric, which is this, contracted, of course, across the velocity. I should say proper velocity, I suppose. And so if we look at the variation, then the resulting equation's coefficient of the proper velocities should be the connection coefficient, right? And so we've got time and then space, space, space to look at variation for. The time variation, we have t maps to t plus delta t, so a of t plus delta t is going to be a of t plus the derivative of a, where that's dA dt times delta t, like that. There's how the variational chain rule of sorts goes. And I wouldn't think too hard about this if I were you at this point, because I don't think they think too hard about it either. Essentially, they just, assume a sort of linearization of the function involved and assume that like delta t is small in some regard. That's essentially what's going on here. I mean, at some point, if you're a math student, maybe you can take a variational calculus class in graduate school and maybe dive into these things more deeply. There is no doubt questions of analysis here which are being brushed over, but I'm not entirely convinced that there's much or any physics to find in those issues. So I'm inclined to kind of just keep going. Anyway, so the time variation here, yeah, gives us this. And so chain rule, I get minus 2 dt d tau, variation of dt d tau. And over here I get 2a a dot delta ij, and then all this times delta t here. Let's see here. Well, Oh. So I was thinking, why isn't there any t dependence here? So in the variation, we are assuming that the t, x, y, and z are independent, okay? So this is a sum over 1, 2, 3, so there's no t in here, which is why there's no like product rule in terms of the variation. Like the variation's just acting on a because a is a function of t, and it's treating this stuff over here as if it was constant, because it is with respect to time, right? We have to distinguish between like the solution we're looking for, where ultimately xi and xj at the level of the solution are going to be functions of t, probably, but we're not there yet. So this is the, so thinking of x or j as a function of t at this point would be kind of like in Calculus 1 when you're doing, related rates problem, putting in the number you're interested in at the start, and then all your derivatives are 0 because you plugged the number in and you removed the variability, So we can't do that. All right, anyway. So we get to here, and then what happens is, over here, I say, okay, well, the derivative of dt d tau times delta t is the product rule, so I've got d squared d squared t d tau squared delta t plus dt d tau of delta t. But this right here I had right there, so I can trade this term for the total derivative term minus that, which is what I do, going from here to there. But so the half and the 2 cancels to leave me a minus, but I get a plus because I'm switching from this side to that. So I'm solving for the this term. It puts that on the other side. The total derivative term integrates to 0 again by assumption, and of course we're still got this term over here. This 2 and the half cancels like so, and there you have it. So this must be 0, and the coefficient, right? So if I look at that, I've got this, right? And then so t is x upper 0. So we've got d squared x upper 0 d tau squared plus gamma 0 rho sigma summed over, contraction over rho and sigma here, like this. And so if you compare these, tilt your head and squint, you can see, aha, there is no dt d tau term here, right? So gamma 0 0 be 0. And, again, there's no dt d tau term here. There's no dt d tau term here, which means that gamma 0, I0, and gamma 0, I0 are 0, right? Much like an elephant, if you look and say it has wings, you can say yes, it has wings. They're just set to 0. In the same sense, these are 0 because they're not here. But these are here. When we have I and j, then yeah, we've got terms, and it's a dot. Yep, delta ij. And then I'm just counting. I can miscount it the first time, so I'm put these numbers over here to keep myself honest. I got one thing here. This is free 1, 2, 3, 1, 2, 3. So I've got 6 terms here, and I and j range from 1 to 3, and so ignoring symmetries or anything, I have 9 Christoffel symbols. So I have fixed 16 Christoffel symbols with this single variation. That is like, man, that's a lot easier than calculating directly from the definition of the Christoffel symbol we had in last lecture, right? Like, yeah, it's a lot easier. We'd have been here all day calculating those derivatives. Yeah. And then the spatial variation, right? And here it is like so. And all right, so what goes on? There is no spatial variation. This is 0. This varies. This goes to 0 because t is independent from x, x1, x2, x3, which are x, y, z respectively. So I'm really just varying this piece over here. Now a is constant because it's got no dependence on x, 1, 2, or 3. So it pulls out, and we just got the product rule, like so. And then notice that I can just put these two together and write it as a single thing by the symmetry involved. I can just put these two together and put a 2 out front. That 2 cancels the half, like so. And then integration by parts. Notice that the derivative of a squared times velocity times the variation is all of this. And so if I solve for what I have here, which would be the velocity times the derivative of the variation, essentially, I think it would be, I've got, good grief, where did it go? I think I got this term here. Yeah, so I'm going to get this term minus this, minus that, which is what I do. So minus 2a, minus that, and then the total, this term right over here, I wrote it down actually, duh. That term integrates to 0, so you're just left with this and that, which gives you, pull the minus out, gives you that and that. And yeah, so that has to be equal to 0, so this is apparently my geodesic equation, which then I'm going to compare to my d squared xj d tau squared plus gamma j rho sigma summed over sigma, like so. And okay, so you look at this and you go, okay, so there's no tt term here, right? So that means that the gamma j00 is 0. There's 3 of those. Let's see here. If I look for just one t being 0, then yeah, that can happen. And I've got xj over here, so that means that 2a dot over a is the gamma j I0 or 0i terms, like I wrote here. Not sure why I still have a 2. Say I have no 2 here. Huh. Well. Let's think about this. I guess it's because this is coming from 0, 1. For example, if j is equal to 1, this is giving me 0, 1, but also the 1, 0 terms in the sum. So if this is both 0, 1 and 1, 0, then this 2 has to go away because they're both, like this plus this has to give me that. I believe that's what's going on here. But so anyway, there's 3 and 3 and 3 and 3, so there's 9 terms here. Well, 9 plus 9, 18 terms. And then finally, it's impossible to have dxi d tau, dxj d tau here, right? There's only time space. There's no space term, which means that the gamma jik is 0. And there's I, j, and k here, all taking 3 values. That's 27, so you added them up. We have calculated 3, 18, 27, 48 Christoffel values here. As you can see, there's definitely an opportunity to get confused about the 2 there. We've got to be careful about that issue. So, I mean, the issue is this. Like, when you're looking at something, this is the same issue if you've got, like, a matrix, right? Like, for example, if you have the matrix, you know, like, let's just keep it simple, 0, 1, 1, 0, right? And you multiply that by, like, x, y, before and after. What happens? See, you get xy, right? Times what? Y. Let's see here. That gives me y. That gives me x. Right, then I multiply that. I get xy plus yx, which give me 2xy, right? So that's essentially the issue here with that too. It's like when I'm looking at this term here, right, it's picking up both the xy and the yx kind of multiplication, which is to say it's picking up the I0 and the 0i. So that's why I have to divide by 2, because both of these are appearing here. And because we are assuming that the Christoffel symbol is symmetric, that's why they have to be equal in half of that. All right, so I think if the Christoffel symbols were more complicated, this could actually involve a little bit more thinking, right? But anyway, there it is. So that's pretty neat. And I was hoping that he would go on and then calculate the curvature for the expanding universe, but he hasn't yet. Maybe he does it in a later chapter. We'll leave it there. That might make a good homework problem if he never does it. So let's see here. So then he says, okay, well, let's consider paths that are null paths in the x direction. So something like this. X mu lambda, t of lambda, x of lambda, 0, 0. So it's going in the x direction, all right? With, so again, null path, so d squared s, ds squared is 0. The metric is 0 along the path. The tangent vector to the path is a null vector at each point, all right? So that gives you this geodesic equation. Well, it gives you immediately, it gives you that dx d lambda is 1 over a times dt d lambda just by solving this, right, for dx d lambda, basically. So you've got that. On the other hand, you've got the geodesic equation, right, which is that d squared x, you know, the time component, d squared x0 of dA lambda squared would be the connection coefficient, Christoffel symbol rather, 0 rho sigma contracted across the velocities like this, right? And okay, so then looking back at the last couple pages, we found out that the only non-zero one, if you got a 0 upstairs, is lower ij like that, and that in fact this was a dot like this. So the geodesic equation actually gives me this, and then I know that dx d lambda is 1 over a dt d lambda, so I put that, substitute this in for that here, and then voila, I've got this, which is the equation that Carol mentions. And he derives it a different way, but this is how I thought I should derive it, so here it is, okay? So there it is. That's the geodesic equation for a null path in the expanding universe. And then he pulls a solution for this thing out of the thin air, and I have no idea how it's done at the moment. Here's my attempt at deriving the solution. This attempt didn't quite go anywhere, but like this is what I was just trying. I was trying to solve this differential equation through some of the techniques I use on things, and it hasn't happened for me yet, right? So hey, if you if you know a way to derive the solution here, I'd be interested. And by derive, of course, I mean derive. As opposed to just check it's a solution. I mean, I can do that. Here's that on the next page. So, is it a solution? Yeah, sure, it's a solution. Right? Like, all right, so like, dT lambda is omega naught over a, where omega naught's a constant, right? A is the scale factor, which is arbitrary, but not given at the moment. So if you calculate dT lambda squared, you got omega naught squared over a squared, right? Great. And so like d squared td lambda squared would be dd lambda of omega naught over a, which would be minus omega naught over a squared dA d lambda. But hey, dA d lambda would be, by the chain rule, dt d lambda times dA dt, which, by the way, would be omega naught over a times a dot, which would be minus omega naught squared, a dot over a dot a cubed. So then if I plug all that into the equation that this allegedly is a solution of, I got myself a d squared t d lambda squared is plus, remember this is the, sorry, this is the geodesic equation we're trying to solve right here. I'm just plugging it into that and seeing if it works. All right, so, and it does, because I got the acceleration term is minus omega naught squared over a cubed. The square of the dt d lambda is omega naught squared over a squared times this, which gives me a net denominator of a cubed on both sides. And what happened to the rats? Oh, my bad. I'm like, it doesn't cancel. It's because I have neglected my a dot right here, which I have earned from this calculation right there, yeah? So they cancel, and yeah, it's a solution. Woohoo! And that's actually, like the physical import of that is actually really fascinating, so let's talk about it. So the energy E of a photon, measured by a co-moving observer in this expanding universe model, right? So the proper velocity should be 1, 0, 0, 0. And Carol's like, that's not entirely, don't think that that's just obvious, because the reason we had to put it to be that, because we wanted it to be at rest, and something's at rest if it has proper velocity squares to -1. And to get a -1 here, we had to do this, to put it equal to the square root of the minus g00 term of the metric, which just so happens to be 1. All right. Anyway, so there it is, and then so the energy of this photon, measured by a co-moving observer in the expanding universe, is apparently omega naught over a. And yeah, that's interesting, and let's explain why. So a photon with energy E1 at scale factor A1 and observed at energy E2 at scale factor A2 will have omega naught equal to the ratio of both of those energies in scale factors. And so this phenomena is labeled cosmological redshift. We defined the redshift Z to be omega 1 minus omega 2 over omega 2. Here omega are frequencies, right? A lot of times physicists use omega for frequency, right? And so like, for example, if the redshift should be 0 if the A1 is equal to A2, right? So if you have, like a photon emitted and then absorbed at pretty much, the same time in the galactic time scale, well then the universe hasn't expanded, and so there's no redshift in that sense. But on the other hand, in this theory, if you have a photon which is emitted at a time when the universe wasn't as expanded, and then it's, it hits something and it's observed at a later time, then you can figure out, you might be able to figure out the redshift of the photon. And wait, how would you know what the original frequency of the photon was, though, right? Well, that's where the astrophysics comes into play, right? So the story goes something like this. There are stars that have particular chemical processes in them, right? And so, there's particular frequencies, spectroscopy, right? Things burn at certain temperatures and so forth. And there's characteristic signatures of certain chemical processes. And so if you observe that sort of DNA of that chemical reaction, right? And the frequency has been shifted from what we observe on Earth to, a lower frequency, in other words, a longer wavelength. It's been redshifted, right? Then you can perhaps extrapolate backwards that, oh, that must have been because the universe was, the universe has expanded since that process happened and emitted and produced the light, right? The light traveled, and as it traveled, the universe expanded, and so now we observe that light as if, we observe the light and observe the redshift, which tells us that the light was emitted from a time when the universe was not as expanded. That's the story, give or take. All right. And there's a lot more to read there. None of what I just said is in Carroll, as far as not what I've read so far anyway. I'm just telling you things I've heard in other courses I've taken, yeah. But if you read page 117 to 120 of Carroll about dust, radiation, and vacuum energy, I think those are worth reading, and we might return to that later. All right, but I think I'm going to focus here. One other thing for this lecture. I'll be brief. I don't have much to share with you about killing vectors. So just a word or two here about symmetry and killing vectors. Appendix B has much more to offer. I'll just focus on a particular aspect. So the claim is that if there exists an index sigma star such that the derivative of the metric with respect to the star coordinate is 0, then translation in the sigma coordinate is a symmetry. What does he mean by that? All right, well, for a time-like path, a particle has 4 momentum p mu mu, as we talked about, right? And if it serves as a test particle, it satisfies the geodesic equation, right? The covariant divergence of the momentum is 0. So let's further digest what that actually means in terms of, 4 momentum. So of course we have the derivative term, which is that's just straight up the proper time derivative of the 4 momentum. Then the term of the Christoffel symbol, if you expand it out and notice that because of the contraction, these two terms cancel and leaves you the middle one. Oh, well, hey, check that out. So this is 0. If this is 0 for sigma star, well, then that means that this drops out in the, in this formula up here. And more specifically, here's the general formula, right? We have mass times the proper time derivative of the 4 momentum is equal to this. So if this is 0, that means that that component of the 4 momentum is conserved. And there's this interplay between conserved quantities and symmetries, which you can study more deeply if you look at something called Noether's theorem, or Noether's theorem. And that leads to what I write here, which is known as Killing's equation. So if we have k equals to the derivative of sigma star, then if we contract this Killing vector over the 4 momentum, that gives us a conserved quantity because the proper time derivative of the 4 momentum in the sigma star direction being 0 is the same as this being 0, is the same as this being 0, is the same as that being 0, and then we can symmetrize. And so lo and behold, Killing's equation, which is this. So a Killing vector is something that satisfies the covariant derivative symmetrization equation like this. And so, yeah, if the metric is independent of a particular coordinate, then the derivative of that coordinate is a Killing vector, and consequently the Killing vector contracted against the 4 momentum is conserved along geodesics. And you can talk about higher Killing tensors, which give you conserved quantities like this. And there's the interplay between Killing vectors and curvature, and Ricci's curvature, and of course the Ricci scalar as well. And this is all very interesting, and I'm shortchanging it here, just throwing it out there. It's definitely worth reading.